The following lesson describes Section 3.5b Exponential Models, Part 2. The goals of this lesson are to review proving something is an inverse with compositions and exploring more examples of exponential models. This warm-up asks you to apply what we already know about compositions and logarithms and exponentials to prove that f of g of x and g of f of x are inverses to each other. Recall to be an inverse, f of g of x has to equal x, and g of f of x has to equal x. Pause the video and perform these compositions right now. The next slide of the video will show the answer to the warm-up. The 5 most common exponential and logarithm models are below. We're going to explore number 1 and 2, which is exponential growth and decay models using E, as well as logistical growth model. This represents the most common models and logarithm graphs. We're going to explore the exponential growth model with E, the exponential decay model with E, and the logistical growth model. In example 1, we're going to find the exponential model that fits the points shown in the table. The points in our table are 0, 1, and 3, 1/4. There are numerous different exponential models that will fit these points, but we're going to find the exponential model that uses E. So recall from the previous page in the notes, y equals a times e to the bx. So this exponential model, our variables are a and b, and we need to solve them. To do this, the first thing you do is you plug in the point 0, 1 and find the equation. So 1 equals a e to the b times 0. When you do b to the 0, you just have 1 equals a e to the 0. We know that e to the 0 is 1, so a equals 1. Now, since a equals 1, we can substitute that back in. So we have y equals 1 times e to the bx. Now we're going to use our second point to figure out what b is. So 1/4 equals 1 times e to the b times 3. To solve this equation, we need to isolate the b. So since we have an exponential with e, we're going to take the natural log of both sides. So when we take the natural log of both sides, on one side we have the natural log of 1/4. On the other side we have the natural log of e to the 3b. Since natural log and e undo each other, that simplifies to the natural log of 1/4 equals 3b. We can divide by 3, and b equals the natural log of 1/4 divided by 3. When we plug that number into our calculator, we get b is approximately equal to negative 0.46298x. Typically, with exponential models, we keep many decimal places. So our final answer is y equals e to the negative 0.46298x. Now, to avoid having to write every single one of those decimal places out, typically we'll use a button in the calculator called the store button. We will store this value as whatever we want. So since we called it b, I would store it in my calculator as b. So we would press STO, which is an arrow, and then alpha apps, which would give us b. And then we'd hit enter. I'll explain more about storing in upcoming slides. As I mentioned in the previous slide, Storing variables is an important part of exponential equations, and I want to show you an exponential model is how to do it. From the last slide, we had our b value was natural log of 1/4 divided by 3, and it ended up being this very long decimal. Instead of having to write out this very long decimal, I stored the value as b. The way you do that is once you've calculated the very long value, you press the store button, which is right here. So the store button is STO, and it'll give you an arrow, which wants you to store it as something. Now I stored it as B. B is right there, which is green. So to get there, you have to press alpha and then the apps button, which will give you B. So you press alpha and then the apps button, and it would store that value as B, which means that B is now stored as that long decimal. Now, if you press alpha apps again, which is what we did up here, there was B, and hit enter, it will give you the value that is stored. It will leave that value stored as B until you replace it with a different value of B. Storing becomes extremely important in exponentials and logs because rates can be very long. So be sure to use this when we're doing these types of problems. Example 2 asks us to complete the table assuming continuous compound interest. So since it's assuming continuous compound interest, we must use the PERT equation. So A equals P E to the RT. Now they gave us a couple pieces of information. They gave us the initial investment, which is our P, and they gave us the time to double, which we will need to use. So we need to use both of these pieces of information to find everything missing in the PERT equation. So if our initial amount is $750, if we double $750, we have $1,500. Now, we don't know what the rate is, so R is unknown, but since they gave us the time to double is 7 3/4 of a year, we can replace that T with 7 3/4 of a year. Now we have to solve this to figure out what R is. So we're going to divide both sides by 750. So we have 2 equals the natural log, no, just kidding, 2 equals E to the 7 3/4 times R. Now because we have the E isolated, we need to take the natural log of both sides. So when we take the natural log of both sides, on the left side we have the natural log of 2. On the right side, the natural log and the E undo each other, and we're just with 7 3/4 times R. Now we need to divide both sides by our 7 3/4. And when we do that, we get R to be approximately equal to this very long decimal point. Now they would like the annual percent rate, and remember the R is written as a decimal and not a percent. So to figure that out as a percent, you can either multiply R by 100 or you can just move the decimal place over. So we know our rate is approximately 8 94/100. However, using what we just discovered, instead of approximating this rate to figure out our amount after 10 years, we're going to store this value, this very long value, into our calculator. I'm going to store it as R so that I can then use that value to figure out my amount after 10 years. So we're going to return to the original problem. So we have A equals our initial investment, which is 750, times E to our rate, which is this very long decimal, which I have stored in my calculator as R. So I'm not even going to type in this decimal, I'm just going to type in R. And then since we want the amount after 10 years, I'm going to plug in 10. So when I go to plug all this into my calculator, remember, I'm going to use the stored value of R. You end up with the final amount of money after 10 years being $1,834.37. $1,834.37. Example 3. In a research experiment, a population of fruit flies is increasing according to the law of exponential growth. After 2 days, there are 100 flies. After 5 days, there are 300 flies. Write an exponential growth model where y represents the number of flies and x represents the time in days. So the first thing we need to do with this example is write the 2 points that the problem gives us. So after 2 days, there are 100 flies, and after 5 days, there are 300 flies. Now they told us it's exponential growth, so we're going to use the equation y equals a e to the bx. Okay. The first thing we're going to do is we're going to take our initial point, 2 and 100, and we're going to substitute everything in for x and y. So we're going to say 100 equals a times e to the b times 2. So we have 100 equals a e to the 2b. Then we're going to take our second point, which is 300, and we're going to say 300 equals a e to the b times 5. So that means 300 equals a e to the 5b. Now these two equations are our 2 equations and 2 unknowns. We still don't know what a is, we still don't know what b is, but now we have 2 equations. The way you solve an exponential like this is you line them up. So we're going to divide 300 equals a e to the 5b divided by 100 a e to the 2b. So we're dividing the 2 equations. We're allowed to do this because they're equal. And so as long as you have 2 equal things that you divide by both sides, you're allowed to do it. So what happens is your 300 divided by 100 becomes 3. Your a divided by a just becomes 1. And you're left with e to the 5b divided by e to the 2b. Now, since the bases are the same, we can subtract our exponents. So we can bring this up by subtracting it. So what we have is 3 equals e to the 5b minus 2b. So when you subtract 5b from 2b, you get e to the 3b. Now, you can take the natural log of both sides. So you have the natural log of one side and the natural log of the other side. So we have the natural log of 3 and the natural log of e to the 3b. This undoes each other, and so you're left with the natural log of 3 equals 3b. When you divide by 3, b equals the natural log of 3 divided by 3. Now, b is a number that you can put into your calculator. In fact, b is approximately equal to this long decimal. But I'm not going to write out that whole huge long decimal. I'm going to store that value as b in my calculator. Remember, we've talked about that numerous times. Now notice I now have b, but I still haven't found a. So I need to take this value and plug it back to either one of these. I'm going to choose to plug it back into the blue equation. So we have 100 equals A times E to the 2B. Remember, B is my stored equation that I had from my calculator. So this is just multiplication. So the way to solve for A is I just have to divide everything by E to the 2B. So I divide everything by E to the 2B. So A is approximately equal to 100 divided by E to the 2B. Now I'm using that stored value, and when I put that into my calculator, I get 48.07498,568, which I'm going to store in my calculator as A. So my final answer for this equation is y equals approximately 48.075 times E to the 0.3662x. I'm going to use these values to answer the next two questions, but I'm not going to use the approximate values. I'm actually going to use the stored values. So leave those values stored in your calculator. The next part of this problem asks us how many flies will there be after 25 days. Now currently stored into my calculator is the value for A and the value for B that we found in the previous slide. So what I'm going to do is I'm going to say y equals A E B times 25. Now A and B are stored values. So when I plug the 25 in, plus the A and the B and the E, I find out that my approximate answer is 454,914.33. Now we're talking about flies, so we can't really have a third of a fly. So we're going to round to the nearest fly. So we're going to say 454,914 flies. By the same token, they are asking us when will there be 5,000 flies. So we need to solve the equation for x. So we have 5,000 equals A E to the bx. Now remember, A and B are just stored values in my calculator. So I'm going to divide both sides by A. So I have 5,000 divided by A equals E to the bx. Now I'm going to take the natural log of both sides. So 5,000 divided by A equals the natural log of E to the bx. The e's undo each other. So we have the natural log of 5,000 divided by A equals bx. Then we're going to divide by B, divide by B. X is approximately equal to 12 and 6/800 days. Now, one thing you can do is when you're doing this problem, you can also graph it, right? So you can graph it and figure out when it hits 5,000, which we've talked about numerous times, or you can do it algebraically. But regardless, you should use your stored values to find the approximate value of x. In this example, the equation has already been given for us. It says, a cell site is a site where electronic communications equipment is placed in a cellular network for the use of mobile phones. The number Y of cell sites from 1985 through 2011 can be modeled by the following equation. This is a logistic model, where T represents the year with T equaling 5 corresponding to 1985. So if T equals 5 corresponds to 1985, T equals 0 corresponds to 1980. Use the model to find the number of cell sites in the years 1998, 2003, and 2006. So the first thing we need to do is we need to do 1998 divided by subtracted by 1980 to figure out what our t value should be. So for 1998, our t value should be 18. For 2003, our t value should be 23. And for 2006, our t value should be 26. Now, you are going to plug this value into your calculator. So you're going to say y equals 269,573 divided by, now you need to have parentheses in the denominator or this will mess everything up. 1 plus 985e to the negative 0.308 thousandths times t, so t in this case is 18, and then you got to close your parentheses. You need to have every single one of these parentheses, don't forget this decimal point, to figure out when t is 18. So when you enter this into your calculator, you get 55,556.98. Now we're talking about cell sites, so you can't have an approximate cell site. So it's going to be 55,556 sites. Now, when you do the same thing for 23, when you plug in 23, you get 147,644 sites. And when you plug in 26, you get 203,023 sites. For this question, it asks you to use your calculator to graph the function where x min is 0, x max is 50, y min is 0, and y max is 400,000. I use my calculator using those windows, and this is the graph. You can sketch the graph in the graph provided. Now, if you want to plot specific points, I have attached the table. Now, how did I create the table? Well, I went to second, which is right there. I went to second, and then table set. Now, table set is second window. Here's table set right there. You can see it right there. And then when I went into table set, I started my table at 0, but delta table I made 10, which allowed my x values to go up by 10. Also, when you enter the equation into your calculator, which I have down here, be sure you have those parentheses that are necessary. If you have a TI-83, you're also going to need parentheses around the e to the x portion. Part C asks us to use the graph to determine the year in which the number of cell sites reached 250,000. So what we did was we graphed the original function, which we had already in our calculator, and then in Y2, we graphed 250,000. Now we found the intersection. The intersection between the two, x was approximately 30 and 65 hundredths. Now here's the question. They want to know what year. Remember, t equals 5 corresponds to 1985. So t equals 0 corresponds to 1980. So we're going to take 1980 and we're going to add 30 and 65 hundredths. When we add them together, we get 2010 and 65 hundredths. So basically, around the middle of the year 2010, there should be approximately 250,000 cell sites according to our model. The last thing we're asked to do is to confirm our answer algebraically from what we just calculated graphically. So we're going to solve the equation 250,000 equals 269,573 divided by 1 plus 985e to the negative 308 thousandths times t. Okay, our first step is to clear our fraction. So we're going to multiply both sides by the denominator, which is a ugly number. On the right side, it just goes away, and on the left side, it's still there. So we have 1 plus 985 times e to the negative 308 thousandths times t times 250,000. Oop, I missed a zero. Equals 269,573. Now, we would like to isolate the green portion. So we're going to divide both sides by 250,000. This is a fairly long decimal, so we're just going to leave it as a fraction. So we have 1 plus 985 e to the negative 0.308 thousandths equals this fraction. Now, because this is an e equation, we need to isolate the exponent. So we're going to subtract by 1. Once again, this is just a number, not a pretty number, a decimal number, but just a number. So we have 985e. This fairly large number, which we can store if we want, or I'll just keep writing it out. Okay, now we need to divide this by 985. When we do that, we end up with e this lovely large number Now we're going to take the natural log of both sides. When we take the natural log of both sides, we have the natural log of this very big number, and then we have the natural log of e to the negative 308 thousandths times t. That just undoes itself, so we have negative 3.08 t equals the natural log of this giant number, which I'm not going to actually rewrite. And then we just need to divide both sides by that. Don't forget the decimal point. When we put all of that, remember this right here is just right there, and we divide it by negative 308 thousandths, our final answer is 30.649, which is the exact same answer we got by finding the intersection. Now remember, the question was what year? So we need to add the 1980. So we know our final answer is 2010.649, which is in the middle of the year 2010. The last thing you need to do is practice. So prove that f of g of x are inverses of each other. Recall to be an inverse, f of g of x equals x, and g of x equals x. Complete this, pause the video, and the next slide will have the answers. Here's the worked out problem for practice 1. It's really important to note that each line has one step. You can only cross out one thing each step you do. Be sure you have all the steps. It is possible to go in a slightly different order, but if you do go in a slightly different order, you need to be sure that it follows the order of operations properly. The order that I have is the most standard way of doing it. Also be sure you have the final statement, f of g of x are inverses because f of g of x is x and g of f of x is x. This is the end of the video. You can now start your homework if you have time.